I'd like to present a project that could change the way how you interact with your mobile phone using a flexible sensing and display cover. And this was joint work done at the Media Interaction Lab in Austria, Microsoft Research, and Joanneum Research in Austria. So in less than a decade, smartphones have revolutionized computing, making interacting with digital information as simple as reaching into your pocket. Although the hardware continually improves, many of the interactions are still reduced to a fairly small and rigid piece of glass. So in this project, we wanted to enhance interaction with existing smartphones without changing anything about the phone itself. Therefore, we picked a widely adopted smartphone accessory, a flip cover, and tried to rethink this form factor, as it can essentially double the area and the space the user can interact with. So we present FlexCase, a flexible interactive flip cover that augments existing smartphones with novel paper-like and gestural interactions. We utilize a flexible epaper display combined with a custom-made input sensor that enables touch and band sensing. This combination turns the phone cover into a versatile input and output device. This talk roughly follows the structure of the contributions we outlined here. We demonstrate a novel form factor that augments existing phones with flexible input and output. We present the resulting design space in multi-display and multi-input configurations, as well as the novel interaction techniques which arise from touch, pressure, grip, and band sensing. We also present some technical novelty in a single sensor that combines multiple modes of input. And finally, we present various application scenarios demonstrating the novel interaction possibilities with our design. Before we delve into the details, let's have a quick look on the key projects in the overlapping areas. E-paper displays are widely used to extend output on mobile phones, mainly with the goal to reduce eye strain and to decrease battery consumption. However, the screens in those products are mostly used in isolation, and the interactions between screens is limited. Mobile multi-display interaction is another important topic and interesting topic of extensive research. Other researchers tried to enhance the interactions beyond the touch screen, for instance, by using interactions above, next, or behind the screen, but also novel input metaphors, such as banding. Inspired by all this work, in FlexCase, we've tried to combine these fields and augment the phone with a bendable interactive e-paper that allows for a much richer interaction beyond the primary mobile touchscreen. To achieve this, we defined a set of high-level design goals. Firstly, compactness. We wanted to preserve the compact form factor of smartphones, but enhance interaction. Secondly, versatility. The device should allow for quick adaptation between different usage scenarios, simple by changing the form factor and adjusting the form factor. Thirdly, expressiveness. We wanted to enable richer input utilizing touch, but also other direct physical manipulations. And finally, portability. The device should be an unobtrusive companion of the smartphone, which should not significantly decrease battery life or increase weight. We experimented with several different form factors, such as attaching a display at the backside of the smartphone or having a detachable display at the side of the phone. However, early user tests revealed that a flip cover form factor would give us the most flexibility. By integrating an additional flexible device into a flip cover, we do not compromise the existing smartphone form factor, but enable various different physical configurations while being folded, and enable the smart cover to be an expressive input and output device. With the e-paper technology, we can complement the high fidelity and high frame rate smartphone screen with good readability in each lighting condition while preserving power and reducing eye strain. The interactive secondary screen of FlexCase consists of an electrophoretic display on top, a printed piezoelectric sensor with a 3x5 matrix, and a self-adhesive protection layer at the back. When deformed, a piezoelectric input sensor creates a surface charge, which correlates with the applied mechanical deformation. And during our experiments, we found that touch creates some local small deformations, triggering one or a few adjacent sensors. Bending, on the other hand, triggers global deformations and a larger surface area and a greater number of sensors. And given this fact, it's relatively easy to distinguish between bend and touch using the standard deviation across all readings and the number of activated sensors. If the resulting value is small, this indicates a touch, whereas a large value indicates bending. Thus, we are able to use one single sensor matrix for both touch and bend sensing without any additional optimization of the layout in contrast to prior work. So summarizing, we can use a single sensor for different input modalities, such as continuously reconstructing the shape of the cover as shown in FlexSense, sensing dynamic touch gestures such as swipes, reading the exact amount of pressure that is exerted on the sensor, distinguishing between front and backside touch given the bidirectionality of our sensor, and tracking touch motions and distinguishing multiple touch points. The design space for interactions composes of several different configurations and modalities which are possible with the form factor. For configurations, we can support book mode, which provides extended screen space, allowing specific content to be offloaded to the secondary screen. And the secondary display can display persistent information, but can also act as a high-fidelity input device for continuous interaction. Laptop mode, where the interactive display can be seen as a keyboard-like input device with a dynamically changeable layout. Backside mode, where the cover is flipped behind the main screen and allows us to use touch, but also continuous band input on the backside of the phone. And closed mode, in which the sensor still provides some interactions through the closed cover. For example, this can be used to transfer content from the smartphone to the ePaper through rubbing, for instance. These configurations can be combined with different input modalities, such as touch and pressure sensing, simple swipe gestures, but also modalities that are traditionally not available on mobile phones, such as gripping and the ability to reconstruct continuous bending of the surface. Additionally, the ePaper display gives us the possibility to enhance interactions with appropriate feedback. So this can be used to either show persistent content on the display, but also to guide the user's interactions with providing changeable output. From the design space, we derived a set of interaction techniques that felt sensible and which are all possible with this single device. For example, pressure and touch input can be used that imagine a hard tap switches between lower and upper case, or rubbing on the backside of the display could pin content. Continuous band input can be used for physically and naturally manipulate linear parameters. When flipped back, FlexCase allows for back-of-device interactions, allowing users to touch, swipe, and bend without occluding the main screen. As both screens are interactive at all times, we can easily enable bimanual interactions with both hands. Moreover, we can use the output capability of the ePaper display to share either content or interactions across screens. And finally, the touch and band fidelity of our input sensor allows for a completely new type of gesture, where the users first grip the device in different ways and prior to bending. And this allows us that we overload several regions like the edge or the corner of the display with different bend actions. So while the first 5 are well-known techniques, now all possible with this one unique form factor, grip and bend is novel and only possible given the fidelity of our input sensor. And this technique will be now introduced in more detail by my colleague David.
So grip and bend is unique and allows you to bend the same area of the flexible display in numerous ways just by gripping the display differently, and our learning-based algorithm can distinguish between them. And we have some interesting technical details here we'd like to present. So in order to detect specific grip and bend gestures, we first wait until a bend gesture is recognized, and this is the point in time when a large number of sensors are activated at the same time, and backtrack and look at the set of data from the last 50 samples. And as you can see here, the gripping and bending phases can be clearly distinguished from another, but also the signals for the different grips. So after locating the point in which gripping occurs, we classify the grip based on the 15 sensor readings, which we average over the last 50 frames due to the noise in the signal. And our first attempt in learning was with a linear class model that consists of a loss function that we try to minimize and a regularization term that should prevent overfitting. So these terms are then defined using a standard softmax model and optimized using a stochastic gradient descent, which we can also use for online learning of new grip gestures. But our model can only describe linear dependencies in the data, which we cannot really claim for arbitrary grips of the phone. So we've continued to look for nonlinear qualifiers, which are usually computationally expensive. So we use a random features to approach to approximate a nonlinear kernel to not look at the full set of data. And the idea consists of using nonlinear mappings to transform a nonlinearly separable problem into a linearly separable problem, like in this figure where we have 2D, a 2D space which we transform into a higher dimension. And after this mapping is computed, a simple linear classifiers can be used to solve the problem efficiently. So in order to evaluate the precision of our grip detection, we performed an elicitation study with the primary goal to extract common grip gestures that are both ergonomically feasible and comfortable to users. And we performed this task with the book style mode, but also with the flick backside configurations with 8 participants. And here you see the nominations of the 2 top gestures for the highest number of occurrences and diversity. But you can find more details in the paper. So the extracted set of grips was then used for evaluating our learning-based algorithm. For gestures both in book, but also for the backside mode, we observed around 70% accuracy with our linear model and around 90% with our nonlinear feature mapping approach. And that confirms the anticipated benefit of using nonlinear classifiers, in particular the random features approach. So now I'd like to show you some of the application scenarios we came up with, which demonstrate a combination of the previously introduced interaction techniques. Here we demonstrate the use of the cover as an extended visual clipboard. The user composes an email, bends the cover to switch to a restaurant recommender app, and then copies content by tapping both on the content and the clipboard. And finally, the user pastes the copied items to the email by simple tapping. In this document here, the user quickly flips through multiple pages by bending an edge, and then the user turns a single page by bending a corner. And then the associated high-fidelity graphics and videos are shown on the LCD, and we use another grip gesture to navigate within the video figure. In the map application, the user can transfer a route to the secondary display by closing the cover and performing a rubbing gesture like with traditional blueprint paper. And we demonstrate how multiple degrees of freedom input can be mapped to 3D navigation in maps by incorporating different grips for zooms, for rotate, and also manipulating tilt parameters. And in this camera application app, all controls are actually located on the secondary display, which leaves the digital viewfinder to be free of clutter. So linear camera parameters such as zoom can be continuously manipulated by bending the corner of the flexible display. But the corners can also be used for changing more than one parameter, such as aperture and exposure, just by distinguishing between the different grips. So FlexCase can also be used to control a background task, such as music by swiping, using a swipe gesture and bending the corner and adjust the volume while leaving the foreground app and the foreground. And finally, gestures at the front and back can be combined together. And here the user pulls back the browser interface, gets an overview, and selects the websites through touch. Okay, so what's next? Our first informal user studies showed promising feedback, but quantitative evaluations in the future could help measure any effects on usability and interaction efficiency. And we've also started to develop a fully mobile version of the prototype, which will also allow us to study its longer-term use in the wild, in the everyday life. And we've also shown many new interaction techniques, but some of the grip gestures to function mappings require some learning on the user side. But we can help the user by directly displaying feedback and hints on the flexible ePaper, and also allow users to define their own mappings on the fly. And nonetheless, we hope we've shown several benefits of overloading bank gestures with different grips to add rich interactions to small form factor devices. So to conclude this talk, let me quickly summarize what we presented today. We demonstrated a versatile flip cover that could actually augment the phone and the functionalities of the phone with new combinations of pressure and grip and bend gestures. And we also integrated a flexible ePaper display that provides additional screen space, but also allows for direct user feedback for the new interaction techniques. And the display can also increase the battery life of the phone when the LCD is used less. And we've also demonstrated a series of interactive applications that combine touch and bend in many novel ways. And we hopefully inspired some people here into rethinking how we will interact with our phones in the future. Thank you.
Questions, please.
Hi, Antonio Gomes, Human Media Lab. This is really great work. I was wondering if you could talk a little bit about your choice for hardware, because ink displays don't have the same refresh rate as the high-resolution displays that you have on the right. Did that in any way influence interaction, especially now that we have touch-enabled flexible OLED screens, if you consider looking into those instead? So that you could actually extend your
I mean, using an ePaper display was really a design choice for that project, because we thought that ePaper could optimally complement the main display, because we have the high frame rate there, which we also need for visualizing and giving feedback for this continuous bend interaction, because that's very important. But on the other hand, the ePaper display is fast enough to show hints, to show changeable user feedback, and also to save battery life. So for instance, in the paper we have one example where we have a boarding pass on the ePaper display, which you can download, and then it's there, and it doesn't consume any energy, because ePaper displays only require energy if you are updating the image. So that was really a design choice.
Okay, thank you.
Zirkl from KAIST. Okay. Hi, I'm Zirkl from KAIST. Thank you for the great work. You showed a lot of cool interaction techniques, but I was wondering, I think the device will be really good for context sensing as well. Like even if you're closing the flip cover and putting in your pocket, the curve of thigh will also make some changes. So I was wondering if you have thought about any more subtle or implicit context sensing interaction techniques or something like that.
Yeah, I mean, what we thought about is pocket touch, so that if it's in your pocket, that you can touch it and that it creates some, for instance, declining a call or something like that. So that could be one option. But we thought it, because on the other hand, it also raises the possibility of false activation. So if the display is always interactive at all times, then you also create the possibility of false activations. So we think that it might be better that it's only activated for several different use cases, as we've shown in the videos. Yeah.
Thank you for presenting today, Kramer Canfield, Cornell University. This is absolutely fantastic. Thank you. Sort of a two-part question. First of all, do you have any plans for patents on this? And second of all, when can I buy one?
I can only talk for the Media Interaction Lab, and we are a research lab, so we are interested in research, not so much in patenting stuff. Yeah. I don't know about Microsoft.
I don't think we patented anything, but we are a research lab as well, although we're at Microsoft.
Okay.
So hopefully the product guys pick it up and maybe, I don't know.
Yeah.
Okay.
No, what we wanted to show is a new way of bringing flexible input to rigid devices, and we wanted to bring up a new design space and that people think about it, and that was the intention.
Yeah, so the beauty of this project is you don't actually need to change any hardware on the phone, so anyone who has skills and wants to put it on Kickstarter could actually build a case which can augment any type of phone.
Yeah. Absolutely. Thank you very much. Very creative.
Hello, I'm Juliana from MIT.
Hey.
Really enjoyed your presentation. So I'm very convinced that the increased degrees of freedom are beneficial that you've created. It's very convincing. Are there particular scenarios where the bendable or grippable input is preferable to the user over traditional inputs?
For the map scenario, what I found in the informal user studies we did is that it's really, really precise for target location tasks in maps. So for instance, if you're searching for a particular point and which combines pinching and panning, and the possibility to continuously zoom, adapt the speed with bending, and the possibility to bimanually pen the smartphone display is very fast. So I would like to do an evaluation on that if it's really faster than target location with pinching and panning.
So last question. What I found really, really impressive was that you guys support a large number of interaction modalities given the really low resolution of the whole sensor. Have you looked at, or how would you tell them apart if they occur simultaneously? Do you support that? How would you support that?
You mean touch and bend?
For example.
Yes, I mean, we've chosen a very simple distinction between bend and touch. So in our implementation, it's only possible to have either touch or bend at one time. But what we could do is, since bend is a global deformation, that we do some sort of two-step approach, so that we first subtract the bending from the surface, and what then should be left is the touch event. So then if we do a two-step approach, we should be able to sense bending and touch simultaneously.
Okay. Cool. Let's thank the speakers again.
Thank you.